Hey there and welcome. Today we're diving into a really cool statistical concept that basically defines what it means for something to be truly perfectly fair. It's called the uniform distribution, and you can think of it as the bedrock of real randomness. Kind of a weird question, right? I mean, on the surface, they seem like they have absolutely nothing to do with each other, but the answer to both actually lies in understanding one simple but incredibly powerful idea in statistics. Stick with me and we'll connect all the dots. Okay, so let's get right to the heart of it. When we talk about fairness in the world of statistics, we're not just talking about some abstract idea. We're actually talking about a shape, a very specific, very simple shape that shows us what a level playing field really looks like. And here it is, the official definition. The key phrase you really want to lock onto here is equally likely. With a uniform distribution, every single possible outcome inside a certain range has the exact same shot of happening. No favorites, no biases, none of that. This right here, this is the soul of the whole concept. Think about rolling a standard die. You know that every number, from 1 to 6, has a 1 in 6 chance of coming up. That's it. It's the mathematical blueprint for pure, totally unbiased randomness. And this is how we can actually see that fairness. Because the probability never ever changes, it's totally constant. If you were to plot it on a graph, you wouldn't get a curve or a spike. Nope, you just get a perfectly flat, straight line, which forms the shape of a simple, clean rectangle. All right, let's peek under the hood and look at the math that actually builds that rectangle. And I promise it's way more straightforward than you might think. We're really just putting some simple numbers to the ideas we've already been talking about. This little guy is the engine room of the whole concept. It's called the probability density function, or PDF for short. This simple formula is what does all the work, calculating that constant probability for any outcome inside our range. So let's just break this down real quick. As you can see in the table, A is simply our starting point, and B is our ending point. So B minus A is just, well, the total range of all the possible outcomes. The formula is just telling us that the probability is 1 divided by that total range. See? Super simple. Now, we're not going to use these next two formulas today, but they're super important properties of this distribution. The mean, or the average, is just the dead center of our range, and the variance, well, that's just a way to measure how spread out everything is. For uniform distribution, that spread is, well, it's uniform. They're really useful for more advanced stuff, but for now, let's get back to the applications. Okay, enough theory. Let's talk about where this thing actually shows up in the real world. Where does this perfect rectangular randomness actually play a role? You might be surprised how often you see it. It is pretty much everywhere fairness is a must. Computers use this principle to generate random numbers. Every time you roll a die in a game of Ludo, you're counting on a uniform distribution. It's the whole foundation for fair card games, and it's a critical tool for building simulations of real-world events. Okay, now it's time to tie this all together with that question from the beginning. We're going to use our new tool, the uniform distribution, to solve a really simple, practical problem at a local coffee shop. So let's pretend we're the manager. We've got a hunch that during one specific hour, let's say from 9 to 10 a.m., our customers arrive at a really steady, constant rate. The arrival time of any customer is completely random within that 1 hour. This is a perfect scenario for our model. So our observation starts right at the beginning of the hour. In our formula, this is going to be our A value, our minimum. The clock starts at 0 minutes. And we're going to stop watching at the end of the hour, which is 60 minutes later. This is our B value, the maximum possible outcome. So our whole range is just 0 to 60. Now we just plug those numbers into our simple little formula. The probability is 1 divided by our maximum, 60, minus our minimum, which is 0. And that gives us a result of 1 in 60. So what does this actually mean? It means the chance of a customer walking in during the very first minute is 1 in 60. The chance they arrive during, say, the 34th minute is also 1 in 60. And the chance for the final minute, you guessed it, 1 in 60. It's perfectly constant. And here is where it all comes together visually. When you plot that probability across the entire hour, you get that perfect flat line, our rectangle. The probability is the exact same at the beginning, the middle, and the end. It's a truly level playing field. So that's really what it all boils down to. The uniform distribution isn't just some dusty old statistical concept. It is our fundamental mathematical model for any scenario where every single outcome has an equal and fair shot.
You know, from a lottery drawing to the timing of some traffic lights, or even the waiting time for a bus, the principles of the uniform distribution are often quietly at work all around us. Now that you know what to look for, I wonder where you're going to see it next. Thanks for joining me.